goodness. All right.
Dr. Jar, are we just doing problems today?
We're gonna talk about covariance still. Why are you?
Okay. Can we talk about the homework too? Because it's really hard. No.
That's not what I like to do.
Okay. Where's my bag?
Did you have a question about the homework? Is that what you were telling me?
Questions about the homework. He's got really high.
Oh, and Marshall's not here because obviously the last class was canceled. So
I saw Marshall. It's mic on.
Dr. Joe, am I allowed to ask questions?
You can ask a question if you would like. Yes. Oh, hey, I guess I should turn on the projector.
And maybe pull the screen down.
No, I'll just leave it on just blackboard. You can see it, right? Okay.
But what if I ask a question and then everyone's like, "You idiot"? How do you do that?
Has anybody actually called you an idiot?
Yeah. Has anyone ever?
Michael calls me an idiot all the time.
That is not with regards to school at all. Ever have I've never called her an idiot with regards to school ever.
So why have you called her an idiot?
Because she just does some dumb things that make me laugh.
It's true. I do some pretty dumb things. Dr. Joe, I gotta show you the problem.
You know what? I haven't even hooked up this thing yet. What am I doing?
Don't worry, guys.
And I spend a lot of money.
Clearly, you're stalling. I know.
Dude. No, I'm not clear. This is actually a serious question that I was asking. I didn't have time to ask earlier because.
You were trying to stall.
No, because I had to have lunch with the recruit. Remember? We talked about this.
Lunch with the recruit.
Yeah, it's a likely story.
So what's your question?
What's your question, Grace?
Well, for this one, it gave us like two sets of integers, and it was like, show the PMF. I was like, and I don't know how to do that. Good morning. Is it the morning?
Definitely not. It's the afternoon.
It just the morning sounds better. It does. Good afternoon is fine.
You don't have to say like.
All right. Anyway, what were you asking me, Grace? Sorry.
Okay, so in this question, it gives us two sets of integers. And it told us to show the joint PMF. And I don't.
Which problem are you looking at?
Number 4 and 4.1.
Okay. So what are your possibilities for selecting the integers?
Aren't there like 25 possibilities?
Well, y is the sum, right? So are there going to be 25 possibilities total?
No, there'd be 13.
Did you calculate 13 possibilities? Is that what you were telling me?
I don't know what you mean by possibilities. Like, they could sum up to 0, 1, 2, 3, 4, 5, all the way up to 12.
Okay.
Okay.
I don't think you get everything up to 12, do you?
Yeah, you can. You get 0 and 0, 0 and 1, 2 and 0, 2 and 2, 2 and 1, 3, I already said 4. You can get 4 and 0.
Okay.
You could get a couple of them twice in several different ways.
Okay.
But other than that, yeah, you can get everything up to 12.
Okay. So what it wants you to do for this particular one is it's literally asking you to graph it. Okay. So what your possibilities for x are 4, 5, 6, 7, 8. Right? 2, 4, 6, 8, and 0, right? We agree?
Yeah.
Okay. And then this goes up to 12. I'm not going to go all the way up to 12 because...
Was I right about that?
Yeah, you're good. Okay. All right. So what it wants you to do is put a dot at where the possible outcomes are. Well, I know that I can only have 0, 2, 4, 6, or 8 for the x, right? So what I'm saying is I'm not going to put a dot where x is equal to 1. Right? I said I'm not going to put a dot anywhere where x is equal to 1 because I don't have any x's that are 1. Because it says x is 0, 2, 4, 6, or 8. Okay. Right? Okay. So I'm only going to have dots along the along the y-axis or line x equals 2 or 4 or 6 or 8. Okay. So what can I get out? What did you tell me I could get out of for the y? So if this is my x and this is my y, what did you tell me I could get for y? You said I could get anything from 0 to 12 for the integers? Okay, so how do I get 0? What do I have to select to be able to get 0?
0 and 0.
0 and 0, right? So I would put a dot there. If I'm going to pick the 0 from this first set and the 0 from the second set, what's the probability going to be that I picked the 0 and then the 0? 1 over 25, because it's 1/5 times 1/5, right? So then you'll put the probability next to that dot. Okay. So to give another example, say you wanted a sum of 8. How can I get a sum of 8? I could do the 4 and the 4.
We can do 8 and 0.
I can do 8 and 0.
Are we supposed to be graphing all of these?
Yeah, I'm going to graph all of them, yeah. And so I can do 4, I can do 4 and 4, I can do 6 and 2, I can do 8 and 0, right? Those 3 possibilities. Okay, so if I do 2 and 4, right? 2 and 6, or 2 and, I'm sorry.
Wait, what?
X is 2, the Y is, what did I say? 8, right? Because it's the sum, correct? So I put about 2 and then 8. Right? Because we were trying to sum to 8, right?
Yeah. So we got a 2 and a...
It has to be the 2 and the 8, right?
Because 2.
So because the 2 plus 6 gives us the 8. So then what we're plotting is, we're plotting the digit from the integer from the first set and then the sum of the two numbers. Okay. All right? And then, this is a weird example. Anyway, and then the other one would be 4 and 8, because I could get up there, right? And then 6 and 8, I would also plot.
One of them you can't have.
One of what I can't have.
Sorry.
Oh, I'm sorry, I can't do the 2. That's my bad. Sorry. It should be 4 and 8, 6 and 8, and 8 and 8. Sorry. Because there's not anything in the 2 sets that they give you. I guess I should write those down. There's the 2 sets that they're talking about. You have to pick a number from the first set, a number from the second set. Right?
Yeah.
And then you're going to plot, what we're plotting is number from the first set, comma, sum of the 2 numbers. So if I pick the 2 and, well, if I pick the 2 with anything, I don't get an 8. That's why I said I plotted it in the wrong spot. 4 and 4 gives me 8, so I would plot 4 and then an 8, right? 6 and 2 gives me 8, so I would plot 6 and 8. 8 and 0 would give me 8, yeah. If I do pick the 2 and the 4, what point would I plot? The 6, yeah, it would be down here, right? Yeah, so we're plotting all of those, and each of these would have a probability of 1/25th, right?
Yeah.
Because we got a 1/5 chance of picking each of the numbers. Okay. For the second part, where it asks you to compute the marginal probabilities, or if you notice some of the other problems, it says write the marginal PDF in the margin. What's the probability that y is equal to 8 here?
3/25.
3/25. It's that sum, right? Those are the 3 ways. So I would write 3/25 in what the book calls the margin.
What?
This is.
Because remember, how do we define the marginal PMF? We add up, for a particular y, we add up all the probabilities associated with the x's. Right? There were only 3 ways to get the 8, correct? X was 2, dang it. X was 4, X was 6, X was 8, not 2.
No.
No, not the 2. Right? X was 4, X was 6, X was 8. Those are the only ways we could get an 8, right?
Yeah.
Okay, so we added up those 3 probabilities to give us the marginal probability associated with 8. Now, in this case, it's not very interesting because every dot that you put is going to have a probability of what? 1 over 25. So those will all have a 1/25th probability associated with them.
So we have to dot all these points, or plot all these points?
Yes.
That's a lot of work.
It's 25 points.
That's not a lot.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're doing like
15 seconds. Okay.
Not that many points. Yes.
So we're taking the number in the first set and adding it to the number in the second set and then finding what those add up to?
Correct. That's what you're doing for the vertical, is what you're added up to. So if I pick 2 and I pick 3, I'll plot the point 2, 5.
Okay.
Oh, I done screwed up.
Oh, you done dude.
You
You done dude. What's a third one?
The more important part of this problem is not getting all the points put in there. It's more along the lines of getting your marginal probabilities. That's what it really wants you to do. Because your joint PMF's not very interesting here, right? To get a certain pair, when I pick the X, I mean, the fact that I'm recording the sum for the Y's, and if I pick the 2, I can't get the same sum given that 2, right? If I have that 2, I get sums of 2, 3, 4, 5, 6. Right? What I'm saying is you don't have, this would be a more interesting problem if they would have done something like this. Well, no, that still wouldn't have been interesting. No, that's still not, that's not more interesting. Sorry. From the,
so they're just kind of like lines, like little itty lines going up.
correct.
Oh, yes.
Yeah, I know. That's what I was trying to tell you.
Well, I just had to get that correct, though. I don't like this problem.
I couldn't tell.
Well, you didn't either. You didn't like it at first.
So you just go to each one.
You just go, yeah. When you're going on 0, what are your possible sums for 0? Associated with the X equal to 0.
1, 2.
Yeah, 0, 1, 2, 3, 4, right?
So this is.
And then you go to 2.
And then you go to 1, and you go to 2 and do the same thing. And you go to 4 and do the same thing.
Do we have to do the same for the X's?
No.
Like the marginals for the X's?
Yeah, it also wants the marginal for the X's.
So do we just kind of.
You just add down instead of add across.
And they'll all be 1/5, right?
25th.
No, I think it'll be 1/5. Yeah, I think she's right.
What?
I think it'll be 5/25 because you're gonna have 5 dots going up for each of them, and when you add them up, it'll be 5/25.
So how is adding in a column the marginal?
Because for a particular X, we're summing it up for all the Y's. So that's the marginal for the X's. It's not a very interesting problem from the probability standpoint. The whole point of the problem is to get you to go across to sum up over all the X's for a particular Y, or sum down over all the Y's to get a particular X. The point of the problem is to try to reinforce the marginal idea and the summing across or summing down, depending if you're doing X's or Y's. There was a point of the problem. This is not an exceptionally interesting one from the probability standpoint, because all the dots have the same probability. Does that help, Grace?
Now that we got that, how are we supposed to know if they're independent? Is it because this?
Well, let's think about it. You can think about it just by thinking about the problem. In order to get a sum of 12, does it matter what the X is?
Yeah.
Yeah. So are they independent?
But it says use that to prove it. Oh no, it doesn't.
No, it
So I
doesn't.
can just say it as
Yeah. The other part is that you can do it from just a simple multiplication standpoint. You just told me that all of these ones for the X's are 1/5, right?
Yeah.
Okay. If I do 1/5 times 3 25ths, am I going to get 1/25? No. So the probabilities don't work for multiplying. You can do it that way too. But you can also tell that your support's not rectangular here, because you're going to have these dots going up and to the right, right? It looks like a parallelogram of dots. Yeah. So remember we talked about this right at the end of class last time. If the support's not rectangular, they can't be independent. Because you've got some impossibilities for one of the variables depending on what the value is for the other. So they actually do depend on one another. So you automatically know they're not independent if the support's not rectangular. Well, and again, the whole idea of that is independent means there's no relationship. If it's not rectangular, there's a relationship between x and y.
I have another question, but I feel like I can ask it.
Why wouldn't you ask it? I want you to ask. If you have questions, I want you to ask them.
Okay,
Yes.
4.1-12,
Okay.
as long as we're still doing this.
Uh-huh.
For part B, how would you do that?
How do you compute the means?
Yeah.
Did you get the marginals? Okay. Well, then you just do them like you do means and variances like we did before. If you've got the marginal distributions for the x and the y.
Can you come check if I did it right?
Sure, I can check if you did it right.
Just like so sad.
Is that right?
Oh, you need the marginals? If you did the marginals right? Oh, you're doing the right process. I'm not going to check your work right now.
Okay, so then we.
So then I would just do the integral from 0 to 1 of x times that to get the mean of the x. Right? Because we're just doing it
From 0 to 1 of this.
of x times that.
So.
Because I'm doing expected value, right? You're just doing expected value of x and expected value of y.
Okay.
If you already have the marginals, that part should be straightforward because that's the same stuff that you did in the previous chapter.
Okay.
There went your eraser.
What?
Alex's eraser went across the room. No, not quite across the room, but
You're a little late there, bud.
just a little bit.
I thought we talked about this yesterday, Sam. I thought you were going to show my time. Come on, man.
I said I was going to show up.
We okay with that?
That's good for step.
Does that make sense, Grace? Okay, cool. Other questions? I was trying to figure out what was going on between you two.
Catch!
All right. Are we happy? Yes.
What's 1/3 plus 1/4?
1/4 plus 1/4.
No, 1/3 plus 1/4.
7/12.
Thank you.
Let's talk about the calculus we had today.
Did everybody? Did you guys get like weird answers for everyone? Okay.
Yeah.
I got like
Oh, yeah.
super weird fractions with roots and.
I was like,
1/20.
What did you get for the last one?
yes.
Yeah.
No.
For the last
Yes.
one, I got.
I got negative.
I second guessed it.
Two over 2, I think.
Yeah. I
That's
got
what
negative
Courtney got.
724.
I got root 2 over 2, 2 over 2
I'm going to
over
use
2.
some dates.
Oh, yeah. Yeah,
That's what I
yes.
got.
That's what
Yes.
So that's not what I got.
Dr. You like calculus, right?
It's fine.
Next, don't catch it. Hey.
Hey.
I want it.
Oh, whoa.
That's expensive!
We didn't grab
My
it.
apologies.
I grabbed
Sorry.
it.
So I shouldn't throw left-handed.
I can't do that, dude. You want me to try? Ready?
No. I would have cried if
That was pretty good.
That was pretty
I would have
good.
cried if it didn't.
That was better. I threw back right-handed. All right.
Cried.
Should we actually do something that resembles probability?
You gotta get scratchy.
No, they don't.
No.
They did very easily. Alright.
All right. Let's do this one.
Wait, Dr. Sean, I'm ready.
Gosh.
Dr. Joe, can you take like another 25 minutes?
Guys, I kept him going for a little bit.
I actually watched his video, so can we?
All right. So what do we need to compute the covariance? Okay.
But we're given it.
So it's the expected value of x, y, and then expected value of x, expected value of y?
Yep.
Yep. All right.
Just need to find expected value of x, y.
Correct, yeah. So in this problem, they give you expected value of x and expected value of y. If they hadn't, what would you do to compute it? If I wanted to do expected value of x, say.
You have to integrate something from 0 to y, and then from 0 to 1.
Okay,
Oh my god. And then 6x
okay,
times x.
Okay.
Yeah.
Thank you.
Right, sorry.
Yeah, that would be how we would do the expected value of x, right? It's the same concept that we did back in the previous chapter. You take x times the PDF and integrate it over your support. It's just that we have a two-dimensional support instead of a one-dimensional support here, so we have to do a double integral. It's the same concept. If I changed it to y, I would do, if I wanted expected value of y, I would plug a y where that first x is, right? Right, same concept. So if we want to do expected value of xy, which is the thing we need to compute for this problem because they give us the other two, what's going to go in front of the 6x? xy, good. So if I want expected value of xy, I'll do the integral from 0 to 1, integral from 0 to y of xy times 6x dx dy. Everybody okay with how we set up, why Grace set up the integral the way she did? Yeah, Morgan.
So it's an integral because it's continuous.
It's because it's continuous, right? That's why we're integrating rather than summing. Yep.
So if we were computing the expected value of y, we're just switching the x and y.
This part would be it'd be a y instead. Literally the only change. Everything else will be exactly set up exactly the same way. Because this part here is describing how the region is described.
Okay.
So that's independent of what you're multiplying it by on the inside. Okay. Everybody understand why the region is set up this way? Are we okay with that? Okay, cool, good. Because usually that's the one that takes me a while to have to explain that. So I'm glad that everybody's good with this. Can I split this up into two separated integrals completely?
No.
No. Why not?
There's a variable.
There's a variable here, right? So I can, even though I can split this up into two separate pieces, I can't split it up into two separate integrals because of this y right here. So immediately, you should be able to answer the question for me, are these variables independent? No. Okay? Because again, the way this is defined, it's not rectangular, right? It's triangular, if you were to graph it. But in particular, given a particular value of y, there are x's that cannot be given, right? I can't get up to that one. Okay? So that's how I know that that's right again. That's how I know they are dependent, not independent. Okay? Now, again, just because it's rectangular doesn't guarantee they're independent either. You actually have to check it then. But if the support is not rectangular, there's nothing to check. They're automatically dependent. Okay? So the only time you have to worry about the PDF being the product of the marginals to get independence is if the support is rectangular. Yeah, Megan.
So since the bounds for x are 0 to y, why wouldn't the bounds for y be x to 1?
Oh, remember, your outer bounds always have to be constants.
Okay, well, yeah.
Right. So that's probably the easy thing to remember is that they have to be constants. But the reason why is because we have, this is our region that we're talking about in this case. Right? When we're doing this, remember, we've got the way we have it set up, we're integrating with respect to x first, meaning we're holding the y constant, right? So we're going this direction, but we think about, we need to take all of these slices that we're doing and add them up over the entire region. So those slices have to move all the way from 0 to 1. Yep.
Okay.
That makes sense? Cool, good. All right, so change back over. Let's see, go through this integral here real quick. This is x squared. So antiderivative will be a 2x cubed y. And then I have to evaluate it from 0 to y. The y is going to go in for x. So really I'm going to end up with, and I'll just do it in a separate step instead of erasing. So we're going to get, what is that? 2y to the 4th? It's 6x squared. And I'm anti-differentiating with respect to x.
Oh, you're multiplying.
Yep.
I thought you're listening.
It's a multiple, yeah. And then this is 2/5 y to the 5th, so we get 2/5. Is that the covariance? No, but it wants you to think it, doesn't it, with that distractor in there? Right?
It's kind of tricky.
It's trying to tricky. All right, so the covariance, we have it up here. What do they have, 1/2 and 3/4? Because I got to scroll up to get this in here. So the covariance of xy will be 2/5. Wow, write a little bit messier, why don't you? 1/2 and 3/4. What? That I can write?
You can math.
I can math? I can, yeah, a little bit. Here and there. What is this? 16/40ths, and this is 15, so a 40th? Did I do that right?
Yes. That is correct.
Woohoo! Very excited. I dressed myself. With little ribbons. You tried.
Good job, Dr. Jones.
Thank you.
Get a participation trophy.
Yes.
Okay.
We okay with that one?
Yeah.
What are you looking at?
My hitting stats.
She
Hey,
just
there's
wanted to
stats.
boast. She just wanted to boast.
All right.
I did it, Dr. Joe. I finished my math before you did.
720.
How do you feel?
All right. So why do we care about the covariance at all?
We don't.
Thanks. Wonderful. Great. Well, see you later.
Tell you like probably favors X or Y.
So yeah, it's a way to measure exactly. It's a way to measure a relationship between the x and y. And one of the, would be the kind of one of the easiest relationships between an x and a y. If we think about graphically, what would be the easiest relationship for x's and y's be? What specific type of function? What would be the easiest kind of function that would a line, right? Some sort of a line, right? Correct. So one of the things that we might want to do, and you may have done this in the statistics course, is find the least squares line or the regression line, right? So let's talk about where that comes from, because my guess is if you've talked about the regression line, you haven't talked about where it comes from yet. If you haven't talked about stats, then you don't even know what I'm talking about, all right? All right, so let's talk about what we're thinking about as far as what I mean. All right, so let's say I have a bunch of dots. I don't know, I may have to cut my numbers down because Grace thinks it's hard to grab more than 20 dots.
It wasn't just me. Don't act like that.
All right, so we have something along those lines. Does it look like there's a general overall relationship of what's going on between the x's and y's? It's kind of up and to the right, right? The up and to the up and to the right. So as x increases, what's going on? Is y increasing or decreasing overall? Increasing, right? So if we wanted to try to get an estimate of what's going on from a line, we would think about trying to graph a line in here that's, trying to approximate the data as much as possible, correct? We agree? Right. In particular, is there a specific point that you think this line might need to go through? Is there a specific point on the graph that you think might be the best point to go through, thinking about how the x's might be distributed and the y's might be distributed? You think there's a specific point this might need to go through? Not necessarily for x's and y's. This line may not hit any of the dots exactly. But is there a specific point on the graph that you think this line should probably hit if it's going to estimate this data as closely as possible? The origin. Not necessarily the origin.
The average.
It should be the average of the x's and the average of the y's, right? I probably should be hitting the average value for each of those things, correct? So this this line should probably go through the mean of the x's and the mean of the y's, right? If it's going to estimate these x's and y's as best as it can, sometimes this is called the line of best fit. If this is going to be estimating these x's and y's as best as it can, it should go through that point, correct? We would hope. Okay? Well, you've done algebra in the past, I hope. Okay? I have a point if I know the slope and I know the point, I know the equation of the line, right? Okay. In fact, you would do y minus y1, or in this case, I should say y minus mu sub y, right? Equals whatever the slope is times x minus mu sub x, correct? That would be if I know the slope. In fact, if I want this point to go through, if I want this line to go through this point, the whole goal of this exercise would be to figure out the dang slope, right? If I'm saying go through the mean of x and go through the mean of y as an ordered pair, the whole point of this entire exercise would be to figure out what this slope is. Right? The whole point of the exercise. Okay? So this would be the equation of the line. Let's assume that we've already found the slope. Okay? All right. Now, given each of these points, there is an error, right? There's some sort of an error in estimation, correct? Because if I plug in an x value here, I get this y value out, right? Whereas I should have got this y value out. Correct? So there's some sort of an error. We agree? So the error, given an x, whatever that x value is, the error in using the using the estimation is just the difference, right? I would do, instead of plugging in the x here, instead of putting the x in try this again. Instead of putting the x in the line, they should have the x for the point. So I would want to do whatever the y value is up here minus what I would get out for the line, right? So whatever the y value is, I would subtract off. Well, think about moving this to the other side. I would have mu sub y plus the slope times x minus mu sub x. Right? Because if I think about this as a function of y, I would move that mu sub y over to the other side. Right? This y value would be what I would get by plugging into the line. The other y value is what I would get from the point, and I would do the subtraction between those two, correct? So this is the y value that comes out of the line. This is the y value for the point, and I know I've got the y kind of playing both roles. But does the idea make sense? This is the y coordinate you would get from the line. And if this is the data point, then the error would just be the difference between those two. Okay. All right. Well, what would be the expected value of this? And remember, our whole goal is to try to figure out the mean. I saw the M and said mean. The whole goal of this is to try to figure out what the slope would be, right? Well, if we think about this as the error, then if I would do the expected error, I would just do the expected value of this. Now, what can I do with expected value relative to sums and differences? I can split it, right? And if I do the expected value of a constant, it's just, what's the expected value of a constant? The constant, right? And if there's a constant times a variable, I can just pull the expected value out, right? So this would give me what? This is expected value of y, if I split it up to here, correct? This is a constant, which is the mean, so I would just have the mean of y, correct? I can pull out the mean, gosh darn it, I can pull out the slope, and then I get expected value of x minus mu sub x on the inside. Of course, I've got these Greek letters in there. What are those Greek letters fancy for? It's fancy for the expected value, right? So what's this going to be?
Zero.
What's this going to be?
Zero.
So this is just going to turn out to be 0. Did that process help us figure out what the mean's going to be? No. It was very, very helpful, wasn't it? Now, if I want this to be a good approximation, I probably want this error to be as small as possible, right? This expected error didn't help me because the expected error is always 0, correct? No matter what line I choose, as long as I make that line go through the average of the x's and the average of the y's, which I agree with Megan is what we wanted to do, right? We wanted to go through the average. That was good. She answered. I'm happy to say it was a great answer. Okay? I can spin that line no matter how I want. I'll still get an expected error of 0. But I think there's lots of different lines there that we'd say would be really, really crappy approximations, right? For example, I probably don't want to use this line, right? That would be a really, really bad approximation for the data. Okay? Why? I don't know. How about X?
X marks the spot, Dr. Joe, so.
All right. So what we do instead, and the reason why we've got this problem is because we just did expected error. The way we've calculated the error is the error can be positive or the error can be negative, right?
Yes.
So instead of worrying about the errors being positive or negative, we need to do a technique that can make the error be always positive. Okay? There's a couple of ways that are easy ways to do that. One would be to take the absolute value. But as you know from a calculus perspective, absolute value can be difficult to deal with because you've got spots where the absolute value can't be differentiated. And one of your things that you try, when you do minimizing in particular, we want the error to be as small as possible. One of the things you do when you're trying to minimize something is to do what to the function? Take the derivative and set it equal to 0, right? So instead of doing absolute value, what's another way that we can make sure that something is always positive? Square it. And what do we call this line again? What's the name? One of the names for it? Least squares. So what we're doing when you're finding a least squares line is that you're minimizing the square of the error. That's where it gets its name from. So let's see how we can do that, and we're going to use some Calc 3 techniques to do that.
Oh yeah.
Oh yeah! That's some Calc 3. All right. All right. Whoa, hey. There we go. Okay, so to make things a little bit easier, instead of writing it in point slope form, I'm going to say that my least squares line looks like y equals a plus bx. And I know I got rid of the m. B is m here, but most of the books use a and b for least squares, so we're going to do it this way. Okay? So then your error will be y minus a minus bx. And we're going to calculate the expected value of the square of this error. These should be capitals just because they should be the expected value of the random variables rather than a specific value. It's more notational than anything. All right. So we want this to be a minimum. Okay. So notice that I need to figure out what A and B both are, correct? So I need to minimize this function with respect to A and with respect to B, which means we need to do what from a Calc 3 perspective? How do we find maxes and mins for functions of two variables? Partials. Now the variables that we're doing the partials with respect to are A and B. Those are the things that we're trying to find. All right? Okay? So these partials aren't that hard. It's just having A and B, right? Now, the other thing that we have to remember is that we're doing expected value. Expected value either involves doing sums or doing integrals, depending if it's discrete or continuous. The important part with that is that derivatives behave very nicely with respect to expected values, meaning that I can just, if I have the derivative on the outside, I can move it to the inside and do the derivative. Okay? Derivatives behave very, very nicely with respect to expected values because sum of a derivative of a sum is the sum of the derivatives. If I have a derivative for an integral, or the variable's on the inside, I can just take it and move it to the inside and differentiate the variable on the inside. Okay? So derivatives behave very nicely. So again, we want to do partials, right? I need to do the partial with respect to A, right, of the expected value. 1, 2, 3. And I need to do the partial with respect to b. Now what do I do with the partials after I take them? Set them equal to 0 and solve the system, right? And just to emphasize here, and then of course we would need to check that it's a minimum. In this case, I'm not going to check it, but if you were going to check it, what would you have to do? Second partials, right? Okay, we're not going to, it works out because the second partials, I think, turn out to be a constant anyway, so it's not a big deal. It's not hard to check. Okay, so again, like I said, the derivative just moves inside the expected value. Move it in here, I've got a squared, so I need to do a chain rule, right? I'm going to bring the 2 down in front, and then take the derivative on the inside. Okay, so if I do that for the first one, we've got expected value of 2 times y minus a minus bx times a negative 1. That still needs to be 0. For the other one, we've got 2 times y minus a minus bx, but in this time we get times a negative x because it's the derivative on the b, right? There's still an x on there. We agree with those derivatives? Whatever floats your boat? Well, I hope it does because it's right. So, all right. Now, these are, you already told me a little bit ago that these are constants, right? And with constants, we can pull them out in front of expected values without any issues. So I might as well take this negative 2 that I see in both of them and divide it over and make it just 0. Don't really care. We agree? Okay. And then I can break things up. So the first one, if I break it up, you get, this one comes down and becomes expected value of y minus, well, expected value of a is just a, and then minus b times expected value of x, that has to be 0. We agree? Okay. Now the second one's a little bit trickier because it still has an x left in it, right? Not bad, but a little bit trickier. If we distribute the x through first, you get expected value of xy minus a times, minus a times expected value of x minus b times expected value of x squared equals 0. Because I have to distribute the x through first. Yes?
It's a negative x squared.
But right, but I divided both sides with a negative 2, remember?
Oh, yeah, because...
Yeah, because I just made, I noticed that those two matched and I just took it out and divided. Okay? So far so good? Okay. I need to solve for both variables, right? The easiest way I think to see to do this is to multiply the first equation by expected value of x and then subtract the equations. Okay? And in fact, what I'll do is I will multiply the first equation by expected value of x and then subtract it that way. Only because something like one of the quantities will fall out that we'll see. So we're going to take this one. Oh, just to make my arrows consistent, that was that particular equation. I'm going to take this equation and multiply by expected value of x. And then I'm going to subtract upward, essentially. Take the bottom one minus the top one. Okay. I get, if I do this one minus that one, we get expected value of xy minus expected value of x times expected value of y. This part's 0. We'll get minus b times expected value of x squared minus expected value of x quantity squared equals 0.
Are you doing this all in one step?
Yes.
Oh.
Whoa, that's like the variance.
Yeah. Yeah, Morgan.
Where did your second term come from? Expected value of x times expected value of y?
Do I need to do it 2 steps so we can see it? I did 1 step. Let me do it in 2. Yeah, okay. All right. So I'll rewrite the bottom equation. this top equation becomes this when I distribute the expected value of x. But I'm doing 2 steps now. Distributed the expected value of x. You got to remember, I'm an algebraist, so I can do the algebra steps in my head pretty quickly. So if you got questions, please ask. Minus, subtract the 2 equations. I'm just glad you're asking questions and that means you're paying attention to me. Well, kind of.
Maybe that's exactly what I'm trying to make you think.
Okay, well, cool, good. You make me feel good about myself, so. All right. So when I do the subtraction now, I get expected value of x, y minus expected value of x, expected value of y. These will go away. I'm going to get plus this one minus, no, I'm not. I'm going to factor out a minus b. I'll get plus that one minus that one. So I get minus b times expected value of x squared minus expected value of x quantity squared equals 0. Ah, so what's this? That's covariance. What's this? Actual variance for x, right? So we get b has to be the covariance of xy over the variance of x squared. If I solve for b, right? Okay. I would add this to the other side and divide. Okay. We agree? Okay.
A doesn't matter.
Oh, A does matter. I just haven't done it yet. I've only found B so far. You Megan?
Well, you have negative b minus the negative.
So I factored out a negative B, so it flips this back to minus again. I would have minus b expected value of x squared plus b expected value of x quantity squared, but I factored out a minus b, so it flips it back to minus again. I promise that's the way the signs work out. All right. So anyway, back to the b again. We're going to figure out a in a second, but back to b again. There's another quantity that you've probably seen that pops up with lost my train of thought. That pops up with the idea of being linearly related, and that's the idea of correlation. Okay, so the correlation coefficient is, use a Greek letter rho to define it. This is equal to the covariance of xy divided by the product of the standard deviation. There are reasons, I'm not going to talk about it today because I'm running out of time. There are reasons why this is defined this way, but it's nice, and you'll see a nice relationship here why, well, one good reason why we might want this way, okay? Because notice I've got covariance of xy here on top, right? If I solve this equation for the covariance, I would multiply both sides by standard deviation of x and standard deviation of y. So I would have rho sigma x sigma y over sigma x squared, right? Or I could write it as rho times sigma y over sigma x, because one of the sigma x's would cancel. Or y over x. And we think a standard deviation is a change, right? How much of a distribution spread it is. It looks like the slope. Spread of y, or change in y, over spread of x, change in x, times this relationship factor. Right? And that slope's going to depend on how related they are or not. And it turns out the correlation always has to be between negative 1 and 1. The closer the absolute value gets to 1, the more related they are. The more linearly related they are. Okay? So the closer this really would get to that kind of true slope idea, or distribution of the spread of y over the spread of x. So this is cool how this comes out with the slope. To figure out what A would be, then of course you would need to plug this in for B and figure out A. That's just a matter of doing some substitution, right? But if I think about it in terms of what we did before, and like I said, I am out of time. Remember, we think about it doing it this way. We wanted to go through that point, right? I don't really need to think about what A is because all I need to do is take out that M and put in the slope we just found. Right? And then we can figure out what A has to be. B is the slope, yep. And then so now you can, if you just move that around, you can figure out what the A has to be, what the Y-intercept is. The A is the Y-intercept. So if I distribute that out and then move the mu sub Y over, you'll get your A will be, it's mu sub Y minus the rho times sigma Y over sigma X times mu sub X. I didn't go back and plug it in. I was just thinking about what the form of the line needs to look like. Remember? We wanted to make sure it went through the averages. Right? So then I could just plug the slope in there. All right, that's how we do this. We'll talk about how we find an equation of a least squares line. Keeping with tradition, I'll be laying out a couple minutes late.
What's new?
What else is new?